the UK space industry is booming, with a huge income of £17.5 billion. We are now one of the biggest satellite-building nations in the world.
And the race is still on for the first orbital rocket launch from British soil.
This month, the Sky at Night team are investigating the incredible science and engineering that's helping us to blast into space.
I'll learn how to build a rocket with a company whose aim is to get into orbit next year. This is the real thing.
Yeah, this will be going to space.
I'll learn how our most important satellites will be exposed to the dangers of space in a brand new test facility. This looks amazing. It's such a treat to be in here.
Radio astronomer Professor Danielle George discovers a sci-fi solution to the impact of the industry on our night skies.
We will match the rotation of the debris, and then we will safely go and capture with a claw.
And our in-house stargazing expert, Pete Lawrence, tells us what we can all see this month. Welcome to the Sky at Night.
Space, as they say, is hard. With something as complex and as powerful as a rocket, there's lots to go wrong. As demonstrated in January by Virgin Orbit.
The historic rocket mission launch from Cornwall last night failed after the rocket launcher one suffered what Virgin Orbit called an anomaly.
And a dramatic end to SpaceX's giant Starship in April.
Starship just experienced a rapid unscheduled disassembly.
These challenges haven't stopped an increasingly wide range of companies, enthusiasts and dreamers from trying to build their own highway to the stars. I've come to Cumbernauld to visit a startup called Skyrora. Wow, it's impressive.
Yeah, so this is where it's all.
Ewan Clark is the project's team lead. He hopes they'll be the first to launch into orbit from the UK. So why are you building rockets here in Scotland?
Currently, the satellites will need to be transported to America or somewhere else to be launched. So building the rockets here means we can launch from the UK. And the other advantage is the orbits we want to go into are ideal for launch from the north of Scotland.
So that's into sort of polar orbits around the Earth. Polar orbits pass over the Earth's polar regions from north to south. This is good for Earth observation satellites, as they can observe most of the Earth's surface over a 24-hour period. And where are we on that journey to orbit?
We have tested the third stage, second stage. The next step is just to test the first stage, and then before bolting it all together, ready for launch sometime later next year.
This is the real thing, right?
Yeah.
This is going to be your first attempt at orbit.
Yeah, this will be going to space.
Should we take a look at the rocket?
Yeah, let's go for a walk.
The rocket is split into 3 stages. I don't think I've ever walked round a rocket before. The top of the rocket is this third stage. This is where the satellite is held inside a payload fairing.
This is the payload fairing, and this is where the satellite will sit. So this is the most important part for our customers.
Each stage has its own engines. So it's its own mini spacecraft, basically.
Yeah, so this is what will take the satellite and deliver it into orbit.
The middle part of the rocket, the second stage, gets the rocket into space.
And then here we have the adapter that connects the second stage with the third stage.
And then the second stage is clearly much meatier.
Yeah, so it's 2.2 metres in diameter and around 4 to 5 metres long. And it's got one 70 kilonewton engine on it to take it just to the edge of space.
And finally, it's the first stage, which isn't on the factory floor yet. This bottom section gets the rocket off the launch pad.
The first stage would be behind me, and that'll have 9 70 kilonewton engines on it, and it reaches about 14 metres long, so almost doubles the length of the rocket.
Yeah, you realise it's a big thing when you're standing next to it like this.
Yeah, it'll be awesome to see it once it's stood upright on the launch pad.
Yeah, when it works.
When, yeah.
Some of the engines on the first stage are undergoing testing in the lab.
So this is our engine bay. We're manufacturing at the moment 3 of our 70 kilonewton engines.
Why do you have these different stages that produce the whole rocket?
It's more efficient to do it in stages. The hardest bit is to get off the ground and get through Earth's atmosphere. So it takes a lot of fuel. So once we've burnt off of most of that, we want to get rid of that weight, and also the 9 engines on first stage. We want to lose that so that it's not holding us back. So we separate, drop the first stage, and then light the second stage. And then once the second stage gets closer to orbit, we can drop that as well and get rid of that unnecessary weight.
So you're sort of carrying only what you need for each stage of the journey?
Yeah.
This first stage is the most powerful. The 9 engines have to get the entire 55,000 kilo weight of the rocket off the ground. What are we looking at here?
We've got the propellants that come in through the top, through the system, the combustion in the chamber, and then out the nozzle, providing the thrust.
So fuel comes out that way, ignites, and then that heads up.
Yep, that's the plan.
And what fuel do these engines use?
So they use a combination of kerosene and HTP. We need the 2 propellants, we need the fuel, and we need oxygen. Because in space, it's vacuum, no oxygen, we need to take our own, so that's where the HTP comes in.
What makes those a good fit for these rockets?
So there's a few factors. They're non-toxic and non-cryogenic, so they can be stored on the launch pad, so it gives us a better weather window. So if we're ready to launch, we fuel the rocket, we can put it on pause for a couple of days until the weather subsides and we can get launching again.
It's beginning to sound very much like a rocket that can take off from Scotland.
Yeah, because you never know what the weather's going to be like here.
What are the things that can go wrong when you're thinking about designing an engine and sending it off into space?
And everything needs to communicate together. So for launch, we need the ground system to communicate with the rocket on the pad and then hand over control. So
it's flying itself, essentially.
That's one of the hardest bits.
Once the first stage has got the rocket off the ground, it's the second stage that carries the satellite payload through the rest of the atmosphere and into space. But the challenge is keeping it on course. Getting the rocket off the launch pad is only the start of an engineer's worries. One of the things to think about is keeping the rocket pointing in the right direction. In the old days, that meant flying something like this gyroscope, which if I spin it and then leave it, if I tilt it, it will always try and come back to the same direction. These days, sensors on board the rocket keep track of how it's moving, report to the onboard computer, and make the necessary adjustments to the engines if needed. Finally, stage 3 of the rocket actually delivers the satellite payload to its final destination. Ewan is giving me a closer look at a test model. Yeah, it's impressive.
So this is 2.2 metres in diameter, and it's not actually the full size. There's another 1.5 metres to go on the bottom of this, so it'll almost touch the ceiling. This will protect the satellite, control the environment around it, and then this drops off just before orbit.
So what are the advantages of this sort of third stage in getting satellites to orbit?
A lot of rockets have 2 stages, but with our third one, it's the equivalent of a taxi service. It'll take you exactly where you want to go, so we can have a lot more accuracy when putting satellites into the different orbit.
The UK is still waiting to launch a satellite into orbit from its own soil, but it has used its own rocket to launch a satellite into orbit from another land. And that rocket was the Black Arrow. The Black Arrow rocket was proposed in the 1960s. The government wanted to see if it could build a rocket based on existing British technology that was originally designed to launch intercontinental ballistic missiles. The launch site chosen was the Woomera Rocket Range in South Australia. After 2 demonstration flights, Black Arrow carried its first satellite payload in September 1970. But the second stage failed to pressurize, and the payload was lost. In July 1971, the program was cancelled on economic grounds. But the latest version of Black Arrow had already been shipped to Australia, so they decided to go ahead with the final launch. This launch was successful, and Black Arrow placed the Prospero satellite into Earth's orbit. The UK became the 6th nation to launch its own satellite into orbit using its own rocket. It also became the first nation to cancel its successful launch program. Instead, the focus turned to the satellites. And 50 years on, the UK has a booming satellite and space industry. And it's something I'm really proud to be part of. I've spent most of my career working on satellites. Missions such as Aeolus, designed to measure the wind speed through the Earth's atmosphere, to the JWST, the largest space telescope ever built. I'm really passionate about what satellites out there can do for us right here on Earth. Until now, the UK has never been able to test its own fully assembled large-scale satellites. But this is all about to change. After 5 years and £116 million, the National Satellite Test Facility is due to finish construction in just a few months' time. And I'm getting an early preview. This beast here is a satellite test unit. Now, it looks absolutely enormous, but it's about half the size of the sort of satellite that will be tested in this facility. When I worked on satellites in the past, they were usually shipped off to Europe for testing. The fact that we have these facilities right here in the UK is really groundbreaking. Now, these tests are crucial because when a satellite is up there in space, there's no going back to fix it. I know from personal experience that this can be quite terrifying. Something you've poured your heart and soul into is rigorously tested, almost to destruction, but not quite. One of the first questions is, will your satellite survive the launch? So I'm starting at the most nerve-wracking part of the facility, the vibration chamber. Program manager Sean Stewart is giving me privileged access. I want to talk to you about sort of the violence of getting things into space. How do we ensure that they will survive that?
So we have two shakers here, a vertical shaker and a horizontal.
So when you say a shaker, well, is that literally what you're doing, shaking?
Quite literally, the satellites, which weigh about 7 tons and are anything up to 8 meters tall, they're experiencing 1.5 G. We replicate all the vibrations from launch right the way through to separation and placement into the orbit.
But there's also quite a strong noise element. I mean, I've felt sort of the noise of a takeoff sort of within my lungs, and that can cause damage too, which people aren't often aware of.
Absolutely. As the rocket's going up through the atmosphere, the skin of the rocket starts to act like the walls of a big bass drum, and that can set up standing waves and harmonics within your satellite, and you can start to cause damage. So what we do here is we build a stack of speakers like you'd find at Glastonbury or a rock concert from floor to ceiling, and then we effectively play music to our satellite. We play all the sounds that it will experience at the levels that it will experience. A Boeing 747 with all of its engines, that's 140 decibels. In here, we'll go to 146 decibels.
At the NSTF, they'll be able to simulate the vibration and noise of the specific rocket used for the launch, from Ariane 5 to the Falcon 9. This looks amazing.
Not many people get to come inside our vacuum chamber, that's for sure.
The next step for the satellite is the thermal vacuum chamber. We've seen the violence of launch, but once it gets into space, the satellite is still in a hostile environment. We're talking about sort of extreme temperatures and vacuum. So how does this facility actually simulate that?
And what we simulate here is outer space. We bring the satellite in, we've translated it through 90 degrees, so it's now horizontal. We shut the door, and then we start to suck the air out.
How about temperature? What range does it do?
So we go down to about minus 180 degrees centigrade, and that allows the satellite to shrink and contract because it's cold. But we can also heat up to plus 130 degrees centigrade, so considerably on boiling water. And we can do both at the same time. So you can have cold spots and hot spots.
I suppose that's important because sometimes you have sunshine hitting one side of your satellite and not the other. And you need to know that it will be thermally stable in that environment.
Very much so.
Sort of cooling and heating. How is that done here?
We have 190,000 litres of liquid nitrogen stored outside the building. And in any 24-hour period, we will use about 90,000 litres to cool this place down.
Wow, it's impressive, but that sounds pricey.
Everything in space is pricey. This facility not only is expensive to be in on a daily basis, you'll probably be in here for about between 30 to 60 days, possibly longer.
Last stop, the Electromagnetic Compatibility Facility. This is the EMC test facility, and it's designed to make sure that your satellite can communicate effectively from space. We're in an electrically neutral zone, or a Faraday cage, and that's achieved by having copper plates in the floor, the ceiling, and the walls around us. It's a great place to test an antenna, to see what the antenna is putting out and also what it's receiving. The walls are covered with over 40,000 of these blue foam cones. They absorb the signals. That means if you want to test your new super secure spy satellite, this is the place to do it, because anyone out there won't know what you're up to. If your satellite makes it through this final stage unscathed, then it's probably ready for space.
Space is a hostile environment, which is why these satellites need to be tested thoroughly. And one of the potential hazards is the sun. Stargazing expert Pete Lawrence is here to tell us how we can observe Earth's star this month.
As we head into summer, the height of the late morning sun means this is a great time to try out some solar photography.
This summer is particularly good because we're approaching solar maximum. This is a period of peak activity that happens around every 11 years, when the poles of the sun's magnetic field switch places. It creates some really exciting phenomena, but it's important to capture them safely.
You should never look directly at the sun, of course, and you should never point any astronomical instruments at it unless you're using certified solar safety filters.
As well as providing safety, these filters help us to see the sun's features more clearly. I'm starting with a relatively inexpensive white light filter and some imagery I managed to capture earlier when the sun was still shining.
So here you can see the sun's visible surface. I can also see some sunspots, and sunspots represent regions on the sun's surface where you have a high concentration of magnetic field lines.
Next, I'm trying a calcium K filter.
And this is where things start to get a little bit more pricey. So the view now that I've got shows the sunspots really clearly, but what really stands out are the bright patches around the sunspot groups and across the sun's disk, and those are known as plage.
Plage are associated with high concentrations of magnetic fields. Finally, I'm going to use a hydrogen alpha filter. This allows us to see filaments and prominences, arcs of plasma being moved by the magnetic fields.
And if I move to the edge of the sun here, I've got a filament, and I can see that that filament extends beyond the edge of the sun, so it's turning into a prominence. And amateurs actually named that, they call it a philoprom. But they look absolutely amazing.
The longest period of daylight, the summer solstice, will take place on the 21st of June in the UK. For many of us, the nights don't get fully dark. This actually helps us to see brighter patterns of stars more clearly, as the fainter stars are hidden. These patterns are known as asterisms, and our summer skies are full of them. At the end of June, the summer triangle moves into position, formed by the three bright stars Vega, Deneb and Altair. The star Deneb marks the top of the Northern Cross, and the summer Milky Way appears to flow through it. Follow the Milky Way south and we can see a familiar shape. This asterism is known as the Teapot, part of the constellation Sagittarius. And finally, to complete the scene, a small group of stars slightly northeast of the Teapot form an asterism known as the Teaspoon.
If you manage to photograph any of the summer asterisms using either your phone or your camera, we'd love to see them. Send them to the Sky at Night Flickr and we'll pick our favourites and feature them in next month's show.
And since we've last been on air, some of you have been sending us your incredible images of the lunar occultation of Jupiter.
But the stars are becoming harder to observe in our night skies. And one reason for this is the increasing number of satellites. I've come to the Glasgow Science Centre to speak to Regius Professor Andy Lawrence from the University of Edinburgh. He's one astronomer who's been particularly outspoken about the threat of the expanding space industry to our night skies. When did you first start thinking about this problem that satellites cause astronomers?
Well, for me, there was a kind of awakening, I would say, in late 2019. Like a lot of other astronomers, I saw an image from the Dark Energy Survey, which had these streaks going across it. That kind of shocked me.
So what are we seeing on the dome? What are these stripes?
Well, this is the tracks of the 100 brightest satellites. So this isn't what you'd see with your eye at any one time. It's kind of what you might see if you were able to integrate on the sky the whole night.
Yeah, they cover the whole sky.
They cover the whole sky, but in reality there's a lot more than 100.
The number of active satellites has increased from around 2,000 in 2018 to more than 5,000 today. So how does the presence of these satellites affect astronomy that we do from the ground?
The big problem is our current obsession is with wide field surveys. So with a big area of sky, there's more of a chance of a satellite streaking across during your exposure.
One of the things that made me realise how big a problem this was seeing a satellite streak not in an image taken from the ground, but from the Hubble Space Telescope. And even Hubble, which is in space, gets affected by this.
Oh, yeah. So both the Starlink satellites, for instance, and Hubble Space Telescope are in low Earth orbit. Satellites can pass within a few hundred kilometres of Hubble.
Satellite trails on Hubble images doubled between 2002 and 2021. And it's not just imagery that's affected. Satellites also create huge interference problems for radio astronomers. What's the solution? If you're in charge for 24 hours, what would you do that would fix this problem?
Well, the solution is regulation. It has to be about trying to work out what a sensible capacity is for low Earth orbit. Although I started from professional worry about the effect on science, I've come to see this as an environmental problem. Up there in space, until recently, it's been almost pristine. And that's been very beautiful and very important. And we're in danger of spoiling that. So I'm a space environmentalist, Chris.
I've always thought of the night sky as a little bit of wilderness that's right there that you can just go out and look at from wherever you are. And I think, never mind the effects on professional astronomy, if the number of satellites increases and we lose that and we're looking out not at the cosmos, but at stuff we've put there, it would just be very sad. It isn't just active satellites that are causing problems. Dead satellites and the pieces of debris they create are fast becoming an urgent issue. A few months ago, on March the 14th, the International Space Station had to make an urgent manoeuvre to avoid a passing chunk of debris. It was the second time that month that Mission Control had to tell the station to dodge and weave to keep the astronauts safe. In the past, astronauts have had to shelter in the station's lifeboats as their home passed through clouds of orbital debris. The point is this: low Earth orbit is increasingly crowded. Keeping track of the thousands of active satellites run by SpaceX and all the rest is one thing, but it's fragments of material from defunct missions that really cause a problem, made worse by missile tests run by the US, Russia, China and India, each of which has blown up a satellite in orbit, creating thousands of pieces of shrapnel each time. You might remember this from the 2013 film Gravity, where the astronauts are interrupted in repairing the Hubble Space Telescope by a deadly debris cloud. But this scenario isn't as far-fetched as it sounds. We're currently tracking 23,000 pieces of debris larger than 10 centimetres, each of which moves in its orbit faster than a speeding bullet. And the high-velocity collisions that they cause can be devastating, and they can cause more problems by creating more debris. This is the so-called Kessler syndrome, a runaway process in which each collision leads to more fragments, which cause more collisions, until the entire orbital space is filled and it becomes impossible to use. Bad news if you want that holiday in a 21st century space hotel, or if you depend on satellites for navigation or communication. The solution? It's time we cleaned up our act in space.
Someone who's particularly interested in possible space junk solutions is Professor Danielle George. She's a radio frequency engineer and has worked on incredible telescopes around the world.
Now, I work on both sides. Radio astronomy, which we know is being negatively affected by the excess of satellites and space junk. But I've also worked on creating satellites that are launched to unravel some of the greatest scientific mysteries. But it's these satellites that, once they're launched and they've done their work, are left in space and add to the problem. I'm visiting a company that's developing technology to help solve the space junk problem. Valentin Valhondo is the program manager. This is incredible. So Valentin, just tell us about space junk. How big a problem is it?
So the way I like to explain the space industry nowadays is if you imagine a highway network of cars moving very fast, over the last 60 years, we have been using it without any tow truck services or maintenance. We are currently developing a mission for the UK Space Agency. In that mission, we will launch a spacecraft and we will plan to remove 2 UK satellites from orbit.
The company are developing a satellite dubbed the Claw. The idea is that it will use a pincer motion to collect pieces of debris in outer space. And so what are you testing here?
So here we're testing one of the critical phases of the mission. We are testing the last approach before capture. On one side, we have the cameras that we will have on the spacecraft. And on the other side, in that robot, we have a realistic representation of the debris that we will want to capture.
Pieces of debris will be spinning in orbit at 28,000 kilometers per hour. The Claw needs to accurately track their motion, and it has to do this in the darkness of space. So how do you determine where the debris is when you're in space?
The sun will illuminate the target, but it's a very directional light. It only comes from a side. We may even have too strong reflections that may blind our cameras. So our algorithms will need to be able to reconstruct the whole motion of the spacecraft only by looking at the part that is illuminated.
Yeah.
After we have determined how the debris is spinning, we will compute a safe trajectory to capture it. We will synchronize the motion. We will have a propulsion system that will fire small thrusters, and then we will safely go and capture with the Claw.
So you're literally sort of emulating how the satellite is moving in space to capture it.
Yes.
If the Claw doesn't synchronize perfectly with the spinning space junk, it could break off more pieces of debris, making the problem worse. Once its prey is safely captured, it can drag it down to a lower orbit, where the debris will burn up in the Earth's atmosphere. I'm really impressed with what companies like this are trying to do. Earth's orbit allows us to study our planet, to send communications and so much more. And it's important that we do it sustainably so that future generations can enjoy its benefits too.
That's all we've got time for, but join us next month when we're meeting the man who's trying to talk to aliens. Good night.
Brian Cox and Robin Ince are back with a witty look at the world through scientists' eyes. The new series of the Infinite Monkey Cage podcast. Listen now on BBC Sounds.